Sometimes the need arises to locate an attribute in Python, such as a function, a method, or a variable, via other means than the import statement. For example, it is a common technique for plugin discovery in PyTest or configuration files, such as pyproject.toml. It can be used in custom software, too. Let's say we have a script that contains the class pre-launch checklist, where a few common steps are defined for a pre-launch diagnostic routine required before a spaceship takeoff. We would like to store the routine descriptions for various spaceship types in a textual data file format, such as YAML. Why? First of all, this will allow us to handle the configuration files separately from the software, as we will not be required to import the mentioned methods during the configuration phase. For example, the checkup routines for the Vanguard 92 Cruiser is similar to the one for the Astra X07 Explorer, but the steps are performed in a different order, and there is no need to validate the navigation and guidance systems, as the reconnaissance cruiser is a piloted spacecraft. The Deep Space Explorer, on the other hand, is an autonomous, unmanned spaceship. That's why it doesn't need a test for its life support system, since it doesn't have any. We would rather store these pre-launch checklists together with other configuration files for the spacecraft, not with the diagnostic software. After all, a list of procedures for a particular spaceship is data and definitely should not be treated as code. Another reason is that we may want to compile a list of callables, each performing a step in the routine, to be evaluated and executed later after some additional preparation and configuration actions. That will lead us directly to the need for validation. The pre-launch diagnostic steps, despite being plain strings in the YAML file, have a strictly defined format. They are fully qualified method names. Each consists of one or more package names and a module name separated by a dot, then a colon, followed by a sequence of nested attributes separated by a dot. In our case, the attributes are the class name and a method in that class. In practice, you often want to be able to validate this notation and spot misconfigured strings well before the first attempt to execute a callable that could never exist in the first place. It would be a shame to perform this complex and time-consuming checkup routine almost to the end, just to find out that the last method name is misspelled, and we need to start over. The very least we could do is to verify that all components of each fully qualified name are valid Python identifiers. We know that in Python, identifiers must comply with a formal and rather complicated description that boils down to the following rules. An identifier must only contain upper or lowercase letters, digits, and underscores, and must not begin with a digit. This sounds like a good material for a regular expression. Let's build one together. First, let's sort out the keywords, which are reserved words that cannot be used as identifiers, even though they meet the formal requirements. For example, we're not allowed to define a method called while or create a class called true. We fetch a list of Python keywords helpfully provided by the keyword library and surround each with a word boundary sequence, marking that we are matching against the whole word. Then intersperse the keywords with a pipe to make sure the rule applies to any of them and join them in a single string. The negative look-ahead assertion will make sure the sequence that follows only produces a match if it's not one of the listed keywords. The identifier pattern, preceded by the keyword detection pattern, can be formalized as follows. A non-digit or a non-special character followed by any number of word characters, that is alphanumeric characters and underscores. The dotted notation we described earlier assumes that the initial identifier can be followed by any number of identifiers, each preceded by a dot. Finally, the complete object reference pattern that will be used to locate the module and its nested attributes is represented by two dotted identifier patterns separated by a colon. Make sure the pattern matches the whole string, from start to end, and the callable pattern is ready. Now it can be compiled and tested against permitted and prohibited names, a check that can fail for a number of reasons. Building this huge and complex regular expression is not a trivial task, and this code is quite difficult to debug and test. Is there a simpler way? There is. Python's built-in string method called isIdentifier will do the work for us. It is enough to make sure that there is only one colon, then break the string up around colons or dots and make sure each component matches Python's criteria for identifiers. Just don't forget to make sure that the identifiers are not keywords. The isIdentifier method will not do it for us. The keyword library has convenient methods for keywords or even soft keywords that, despite being reserved, are allowed to be used as identifiers. We can easily make sure this method works the same way as regular expressions, succeeding and failing exactly when it's supposed to. There is one more practical issue to be addressed: computational costs. With the help of the time library, we can develop a simple test that will calculate the running time of the regular expression match or the string fragments assessment, depending on the method passed as the second argument. We're not interested in the results of the method call. All that matters to us now is how long it takes to process a string using one or the other method. Note that we've chosen the perf counter and s function from the time library, which is a better choice for benchmarking than the time function, as it has a higher precision and will return the result in nanoseconds. We register the time before and after the string processing, then calculate and return the duration. Now, to the tests themselves. First, let's conduct the experiment with generated strings of increasing lengths. For each number from 10 to 100 million, we'll construct a fully qualified name whose length, as a simple calculation show, is 20 times the multiplier value plus 3 for dots and a colon. For each length, we want to find the difference between the regex matching and the identifier detection. To convert the result from nanoseconds to seconds, we'll multiply it by 10 to the power of -9, and we'll keep in mind that the negative result will indicate that the regular expression is faster. The output precision up to 6 decimal points must be sufficient for our rough test. Running the test may take a long time, so we'll just show you the result from one of our previous runs. It indicates that the difference starts to become noticeable when the length of the analyzed string approaches millions. But who would write a method name that's several million characters long? A more realistic scenario is a large number of shorter, fully qualified names, each approximately the same length. For each length value, we'll construct a list of names of that length and measure the running time. First, for the regex.match method, called on each name in the list, and use the same method as before for obtaining the timestamps in nanoseconds. Then, for the validate function that, as we remember, uses the isIdentifier and the isKeyword methods. As before, we find out the difference in durations, convert it to seconds, and, keeping in mind that the negative result indicates a better performance of the regular expression match, print out the difference with the same precision. The running time will be noticeably longer now, and will speed things up for you again. The results may vary a little from run to run, but they show nonetheless that the regex begins with a marginal advantage, but closer to 1 million of names its benefits are starting to become apparent. When we're analyzing tens and hundreds of million strings, you may decide to rely on regular expressions because of their higher performance, despite them being difficult to write and maintain. Remember that our analysis is far from complete. For example, we could somewhat speed things up by rejecting strings with the wrong dot and colon pattern right away. In practice, you'll notice what kind of errors occurs more often, and we'll guard specifically against these cases.